So now it is my pleasure to introduce Clarisa Sánchez. Oops. She'll talk more about machine learning, deep learning, and medical imaging. She's associate professor at the Radboud University Medical Center in the Netherlands. She actually obtained a PhD here in Spain at the University of Valladolid, working more in retinal image analysis for diabetic retinopathy screening. Then she did a postdoc at University Medical Center in Utrecht, and currently she's leading the research line focused in computer-aided diagnosis in retinal images. So please welcome Clarisa.
Hello, thank you very much. I would like to thank the organizer for inviting me. It's a pleasure to be here. And I'm going to explain a bit what we are doing, but also I would like, thank you. I would like to show you some examples of challenges that we are dealing with. So, we are working in this group. This group is very focused on the interpretation of medical imaging. And what we are trying to do is to help the doctors, and I said help the doctors, to make the interpretation of those images. And we have a different focus. Well, we are in breast for breast cancer, or we are doing in lung for lung cancer, or retina. That is the group that I'm leading. And we have seen a revolution. We have been working in this field for a long time now, and there has been a big change, that it came with the hype, we can say, or the deep learning boom that there has been like a few years ago. So we go back how we were doing now. We were working with pattern recognition. With pattern recognition, what we did was basically this. We have a medical image. We have some training samples. We just look at the data. We think about the problem. We create some features. We define them in a way that the computer can calculate it, and then we train it. We learn the problem, and then we just apply to the medical imaging. And for that, before deep learning, we were doing something like this. So we sat down in front of the computer, we just look at the data, we just think about the problem, and then make the features, and then we obtain the output. And then we created work or publications, or we did things. For example, in this case, was for two types of lesions, one in retinal images and one in CT scans. And for the retinal images, you can see there the long list of features that we were calculating. And it was, up to, I don't know now, it's almost 100 features. And then, this was only for one type of images. This was only for one type of features. But then deep learning came. And in that, we replaced to this. We just have to give all the images, have a good architecture, think about the problem, maybe introduce some a priori knowledge, and then we will have the output. And then we managed to do things like this. So from a pathological image, this image from a biopsy, we will get, without giving any kind of features, we can distinguish all the type of tissue that is in this image. Or we will have something like this, like we can segment the vessels in the brain, and then we can even see the flow in order to distinguish areas where might be a blockage or it might be an abnormality. Or with retinal images, we even went a bit further where we did different tasks, like we did the registration of different type of images, we calculated some, we detected some abnormalities, and then we come up with some measurements in order to help in the decision-making of the doctors. But this is not new. To be honest, this deep learning part has been there, or this neural network has been there for a long time. This is from 1995, and this is for breast cancer, and then they use that. They use it for calculating this kind of features. But the problem is that, the situation is that the change came when this was all together. We had the data, now we have more access to the data in a way that we can access it. We also have the neural network, they all were combined, but also we had the computational power. And then the magic, in brackets, appears. So we saw, and when we were working on this, we saw, okay, we will need to do this. Let's see what is happening. And then we did a survey because we were seeing like a hype. And what we saw is like in few years, we can see that everything started in around 2010, especially in computer vision, 2012. Well, it came later in healthcare. And we saw that there was like a boom of publications using deep learning. And not only with the publication, it was also a boom in the type of problems that they were tackled. So it was solving problems like classification for the images, for the detection, segmentation, but also others that they have been extended. I'm going to give you just a small overview of what the problems that they were there in that time, because this is a review that we did in 2017. So things has changed a lot in the last 2 years. But I'm going to show you exactly what we saw. So for the classification of medical images, what we were doing is like, or you introduce an image, the whole image, and then you have to make a decision. Or you introduce, we can say a lesion, and then you also have to say the decision. For the image, it could be this is normal or abnormal, or for example, in this case, for the nodule, it's malignant or not. And we saw a kind of a challenge. The first thing is something that has been tackled is like, well, we don't have so many training samples, and it's true. Maybe we have a lot of normal images because there are a lot of images in the PAC system in the hospital, but there are not so many with the pathology. So that was a problem. Also, we are dealing with images that are completely different from computer vision. This can be 3D images, 3D masked temporal images, and then we have to deal with that also. And of course, it's very important, the contextual information. And with contextual, I'm talking not only about in the image itself, but also the context of the patient, like the age, what is happening with this patient in general. And there were proposed some solutions. For example, the typical solution you have been seen if you read one of the papers that they have been published about the classification of medical images transfer learning. You train the image, the network with this huge data set of normal images or visual images, for example, ImageNet, and then you just transfer to the medical imaging. Or we are also seeing like we have created a specific architecture like 3D convolutions or multi-stream convolution in order to tackle with these things. One of the publications that gained a lot of traction or gained a lot of attention was this one, that this was for the classification of we can say like tumor or for the classification of the skin. And it was shown that it got a very good performance in a very large data set that they analyzed, very good performance, even comparable with dermatologists. Another thing that has been done in medical images is the detection. And with detection, I mean, you give, like in this case, it's a CT scan of the thorax, and then you have to find nodules. You have to specifically identify the position, and then after that, you can make some measurements based on that. And of course, there is a big challenge here. You need to go through a volume that this, you don't know, it can be 3D, but it can be also 3D mass plus T. And it's a problem because it's a needle in the haystack problem. You have to find a small nodule of millimeters in a big CT scan, in a big 3D CT scan. So, of course, there were some solutions that the community came up, and some of them were using novel architectures. For example, you have heard of recurrent neural networks, and they were using those ones in order to parse through the whole volume, and it was applied in this case. Or applying weakly supervised algorithms or training strategies in order to deal with this problem of searching in a haystack. And for example, this is a work that we did in where we tried to do a selective sampling in order to just select those samples to train in a dynamic way the system so it can learn faster how to find abnormalities, in this case, in retinal images. Another thing that is also a task that is being done for doctors is the segmentation. The segmentation, what we want to is to detect the area. For example, in this case, you want to detect a part of in the CT scan. You want to detect where exactly it is. And of course, the challenge here is that it's huge. You are talking about voxels. You also have to take into account into context. So you are classifying a voxel in an image, but you have to take into account where the voxel is. So you have to deal with different, we can say, scales, and also taking into account connectivity. Like, okay, if a voxel is inside the liver, well, you have to classify also probably the next voxel inside the liver. And then we came up, or the community came up with architecture that are very focused for this one. Everybody heard about UNet. I'm not going to explain it here, but other architectures that go and use, and also regularizers. For example, a nice application of GANs, of generative networks, where you make two networks compete against each other is, for this case, where you put a classification and segmentation network, you get a segmentation, then you have a GAN that try to identify if this segmentation is created by the computer or is created by a delineation from a human. And of course, these are specific tasks that they were there, but there were other more that are especially coming now after this kind of problems have been solved. And I'm going to say solved in a very doubt, because I don't think it's still solved, but it seems that we are getting a lot of good results there. So now new problems are being tackled. For example, we are combining the images with other non-imaging data, for example, with text, or we are combining with genetic information. Of course, the registration of images is something that is not from computer vision, it's very typical for medical images, and we are also doing this. Synthesis is something that has been discussed also, has been mentioned in a way that you generate data. For example, if you want, you have a low dose CT scans where the patient receives a low dose, you get a CT scan that is quite blurry and quite noisy, and you can generate from those low CT scans, you can generate a high dose scan. So in this case, this has been done also there. And also we are using it now more and more into prediction. And in prediction, for example, this is an example that we are doing. This is this is an abnormality in the retina that grows with time, and it's important to know how this happens and where it goes, because if it's involved one part of the retina, then you can get blind, and then you need immediate action. And you can see that given the baseline image, so the image at this time, you can try to predict what is going to happen in 5 years' time, and you can see there the output of the network. So this is very fast, what is possible then, so you can think about classification, segmentation, and it's all about feature extraction and calculations. And there are successful stories, of course. These are all publications that have been done in the last years, where it's like big studies with big data sets that they get very good results, and they compare with the performance with, for example, radiologists or ophthalmologists, and they get very good similar results than those doctors. And many of them have been already integrated, so they have the FDA approval, so they are ready to be integrated in the clinical practice. And well, the funny part is that this was an overview that was done in January 2019, and in April 2019, there were already 10 more systems that were FDA approved. But is it true? Is this a successful story? Well, I'm not sure about that. For example, if you look at the list of publications, only few of them, the one with the star, are the ones that are being assessed in prospective studies. The rest are all retrospective studies in a way that you just take the data, you have a controlled data set, you probably select also the data where you have like, an amount of normal, amount of abnormals, and then you apply and compare to doctors outside their practice, because you just tell them to do what they have to do for that task. So, for example, this is a publication that was in May 2019, and it's from Google. And then they just show a network that can predict lung cancer from CT scan. And what they claim is that they are outperforming radiologists when a single CT scan is shown, and they are similar to radiologists when more data from that patient is shown, when previous scans are shown. Of course, when we reviewed that, there was a replication to this, and there was a reply to the thing where they show different things. First, it was a retrospective validation. Again, it was a selected data set that was just used for this, and it was used in the same population, so it was We can say you select the data, and then you just divide your data in your validation and test and your training set, and then you just calculate it. This completely overrules, or as they propose, it overrules what is the well-established clinical guidelines. The doctors follow guidelines where they have to check several things, and they do this in order to make a decision, a clinical decision. And this completely overrules that because it doesn't relate to that. So it's completely outside what is the clinical practice. Also, they compare with non-thoracic radiologists. Usually what they do is with radiologists that are specialized in this kind of task, and they are really good in this, the tasks that they are asked for, and in this case, they compare to radiologists. They don't show, well, they don't they say that it can be reproducible. They, of course, don't give the code because, or they don't show the access to the code. But it doesn't see how it can be reproduced, and we are again in this black box course that is harming so much our field. And then it's not clear how they are going to integrate this in the clinical setting. But this is a problem. And the problem is that you heard a successful story, you think like, hey, the problem is solved, but the reality is not. The problem is not solved. It's not even there. So most of these problems, most of these publications that are out there talking about we are going to replace doctor, everything is solved, the reality is like only of them, well, first, only a small part of the clinical tasks that the doctors are doing for one image is covered. It's just that, nothing else. And it's a very well-defined problem with a very clean validation set. So it's not the real practice. It's not what is happening in reality. Then it's not, there is a lack of proven clinical efficiency. We measure accuracy, we measure sensitivity and specificity, but what does it mean in clinical practice? It's really showing that the patient benefits from that. It's really showing that we are improving clinical practice. Well, that's not really what is being shown now. And it's a control validation. And the last part especially is that there is not a prospective study. It's something that is being done in retrospective and in the data collection. And only 5 of the 27 studies, although there are more studies, but those big studies, only 5 of them are trying to do the prospective study. And the reality is in those prospective studies, the performance of the system is much lower than what was done in the retrospective studies. So are we there yet? Unfortunately, no. And I think that we have just started this integration between AI and humans for healthcare in this case. So, and this has been also covered by one of the godfathers of deep learning, Geoffrey Hinton, where he said, like, of course, like in 2016, he said immediately, okay, forget about training radiology. It was like a shock for all the radiologists out there, forget training there because they are going to be replaced. But now in 2018, he said, well, wait a moment. We have seen a lot of inaccuracies in this system and we have to be a bit careful with that. And I agree with that. So what do we need? What do we need to make this happen? Well, first of all, we need to continue keeping doing these algorithms and trying to see how we can adapt those beautiful architectures that are being done, how we can adapt it to what we are dealing with in healthcare and how we introduce it. Please keep on doing that. But of course, we also need more things. We need to invest a bit in data and in annotations. And in data, I mean, we need to create this data set that it can be reused. Hospital has to invest in this type of data sources or data sets that it can be reused and it can be used between different hospitals, in between different researchers in order to improve what we are doing, in order to see the variability and how the systems behave in this kind of settings. Also, we need to make annotations. And this is very important. We sometimes forget about it. We only think about data sets. But the reality is that we need to make the annotations because it's where the knowledge comes from. It's not only the data in this case, it's very specific. We are dealing also with that, and it's like something that, for example, you don't get funding for or you don't get support for because, yeah, well, annotations are there. But it's true, we need to train first the doctor to make the annotation because it's a way to pass that knowledge from the doctors to the computers, but also to train our algorithms. Then we need validation strategies that demonstrate the clinical efficiency. And it was nice that Emilie presented at the beginning, well, a smarter system needs a smarter validation. It's completely true. We need to see how these systems behave in this clinical practice, in these clinical settings. And we have to support this retrospective study. That is a lot of work, but we need to support it in order to see how AI is going to impact healthcare. And of course, we need to promote challenge and reproducible science. You have seen a lot of this challenge, the big challenges that are there. It's important because, for example, there was a big one for lung cancer, where it was publicly available. All the winners make the code publicly available, and the data is also publicly available. It's important to have that in order to compare, in order to see if we can combine and get better, in order to push science further, not to be proprietary and not share. Of course, there is a need to change in regulatory entity. And why I say that? Well, it has been a change now. We can see that the FDA has changed, making it very difficult to really approve this kind of healthcare AI solutions. Now they have like a fast track to deal with this kind of solutions. But of course, now what they are asking for is that you freeze your algorithm. And in that freezing is when it comes all this thresholding, it comes these things that are not changing. And we are really cutting the wings to what the AI are. AI learns and learns every time more and more with more data. And now those systems that are dynamic are not covered. They are now thinking about it, and in 2019 April, they are trying to make this happen, but of course it's very difficult to try to regulate something that changes over time. But let's think about this. Doctors change over time. They are introduced when they are young. They are supervised by the senior doctors, and they learn with the time. And we have to also deal with that. One thing is important, and we are always missing, is that we need to educate the clinical personnel in AI. And we, as scientific personnel, we are responsible of doing that. There is this black box curse. That is true. Sometimes it's true. I mean, we don't know sometimes why the systems say like, okay, this is malignant, or this is benign. Although later it's going to be explained how we can do that. But one part of this black box curse comes from the no knowledge of what is happening with AI, and no understanding how AI works or what is behind that, or what is the effort. So I think that it's important that we also educate the clinical personnel in AI, because they are going to use it, and it's going to be their third hand, we can say. So they need to learn about how to deal with it, what to expect from that, what is the possibilities, what are the challenges, what are the limitations. And the last one, I think also what we need is to create a healthcare AI environment. And with this, I mean, this one that it was presented in one of the conference in radiology. It's important that these solutions are not far away from the reality, from the clinical practice. We need to take everything inside the clinical practice, and we have to create an environment where everything can fit each other in a way that we can create the software, we can validate the software, it can be tested, it can be check how the doctors behave or how they change their opinion, and we can retest and redo. Nowadays, this is completely separated. We have the scientific people, technical people working in a place, in an office, doing this kind of solutions outside the hospital, far away from the patient and the clinical problems, and then we expect that those systems need to work as good as the radiologists or as good as the ophthalmology. We are completely separated. We need to go inside. We need to become the system if we want to change the system. So I think this is an important message that we have to deal with, and we have to support this for the change. And are we there yet? Well, as I say, unfortunately not. Of course, we are not there when now, before a long time ago, I remember when I started doing this system, doctors were, come on, no, I'm not going to use this. Well, we are not there. Doctors are no more willing to use it. The society is also more willing to use this kind of solution, what is really good. But of course, we are not there yet, when we have to think, hey, what do we do now? The system says something wrong, and who is the one that we have to sue? I think that we are not there yet. We are somewhere here, we have started, but it's promising. But it's our responsibility to make it happen. And I really think, and I think I agree with the previous speaker, with Bart, that we are not here to replace doctors. We are not here to replace how the clinical setting is done or how healthcare is there. But definitely, we know that the clinicians who use AI, we are going to be replaced for those ones, with those ones that don't use it. So thank you very much. Are there any questions?
Audience?
Maybe just one thing, as you said, we need a lot of data, which definitely is true. Then you say we need annotations, which is true, but I'm not completely sure that's fully true. So I want to know your opinion a little bit with regard to what we call like supervised versus unsupervised data, because I mean, in a way, when you're a researcher, you're collecting data, you don't know what you're looking for, and you try to find patterns. So maybe by having annotations, we can try to learn things that we currently, when you do annotations, by definition, you use the current knowledge, and you will never learn new knowledge in some ways.
Yeah.
So how do you see that, the role of kind of unsupervised learning?
Well, I think unsupervised learning is something that as human we do. As when we are kids, it's something that we do. We learn in an unsupervised way. But we are talking now as a specialization. It's very specialized knowledge. It takes years for them to learn, and they learn with examples. Maybe not annotations in a specific, all the voxels, maybe not in that way, but some kind of annotations. And I think that's what I meant with those type of annotations. We need some kind of knowledge that it needs to pass from the doctors, that they acquire from books or from teachers, and need to pass to the systems. I think that we can, so far as we have seen with our experience, and supervised solutions completely outperform unsupervised solution. And I think that if you can create good annotation and you can invest in good annotation, you can get very good performing systems. Unsupervised is very nice in a way that it solves problems, it can be there. But if we can collect the annotations, why to make it difficult in that sense?
So along these lines, my question won't be that technical, but it's probably more philosophical or logistical. Okay. So you mentioned that hospitals and other institutions should actually have the data in a fair format, or you should encourage doctors and hospitals. And so I wonder, I mean, how do you think, what are the necessary steps like to get that done? Should like public systems like the one here or in the Netherlands, I don't know how that's organized. So how do you actually get to that point where hospitals make that a priority and they have the right people with the right expertise embedded in their teams to actually accomplish that? Because I think that's one of the most difficult challenges nowadays.
Yeah, I completely agree. And I think it's going to be discussed during the panel. I think that it's a big problem, because I think that with these systems, with AI and with deep learning in this case, we are going to a situation where we need data from different patients. Doesn't matter. There is no name we can say of the data. No, we need data. We need to go into it. We have to learn from that. And in the other hand, in the other spectrum, we have the privacy for the patient, when everything gets closed, when everything cannot be shared, it needs to be protected. And then we have those two things that are now we are dealing with. It's very difficult now to work in a hospital in a sense that, you have to deal with a lot of regulations, how you can treat the data from the patient. And there are things that you cannot use, and later you cannot maybe test it in a different hospital, but it needs to be a chain there. How to do it? Well, we can discuss it during the panel. I have my ideas. Of course, we can create safe haven where the data is all collected and it can be accessible for other researchers and other hospitals. But that requires a change in the infrastructure, a change in how the data is collected right now, how it's safe or how it's used. So yeah, I think it needs to be a big change, and it's a big challenge nowadays. Yeah.
Okay, other questions? There's a question there.
Thank you very much. My name is Naila Siddiqui Kamal, Senior Lecturer at Imperial College. I totally agree with what you've said, and I'd just like to add a little comment because I'm a clinician. Gynae cancer is my specialty. And I took on to artificial intelligence quite late in my career. And that was simply by recognition that, there is no other way to deal with the challenges of today's healthcare. So a few points that you had spoken about, the system needs to be aligned, all ducks aligned together in order to make this model work. And that actually to me looks like a learning health system. Mm-hmm. So the question asked previously about how do you engage clinicians, because this is the biggest challenge. There are two main challenges. From the technical side, we see everyone is very keyed up to bring new disruptive technologies. You have the big names like IBM, you have IBM Watson, and the big race is on. But what is the roadblock? The roadblocks are clinicians' mindset, and the second is the patient engagement. These are the two very non-technical things which are really stopping the speed of change. Mm-hmm. So for a clinician, there are three important things, where AI can play a role and what you alluded to. And I'll just highlight what is the real challenge which I think people should focus on. So three things are situation awareness, and second is the critical thinking, and third is the timely decision making. These are the main skills for clinicians. So the first one, situation awareness, and the last one, timely decision making, AI fits in. But the bit that is difficult is the middle one, which is the critical thinking through the data set that a clinician has in their mind. And how do you teach a machine to think exactly, touch on those points that a clinician would be thinking about in that particular aspect? Yeah. So that is something that I'd like to know how we are going to achieve.
I think I agree with you. There are big challenges there. And I think it's a mistake to think that with AI, we need to replace, we need to change. I think that's a big mistake, because I think that we are never going to replace what doctors do, because there is more out there. There is knowledge, there is an intuition, there is a, it's what you said, the patient enter in the room and the doctor is already collecting data, is already having an intuition. And that's something that is going to take many years that happens. So I think that we should take out from our mind the idea of we are here to replace doctors. We are here to augment doctors. That's the reality. We are here to make doctors better. And that's what we have to think. And that integration, how we can use this system to integrate in the clinical practice is what is needed. I think that all this solution is what we show in the paper is always doctors versus machine. It's like computer AlphaGo. It's like playing AlphaGo. We are not playing against each other. We are not here to win. We are here to a different thing. So we really need to change that mindset, and it's a challenge.
I think indeed this is important, but let's discuss this further this afternoon, because I think the aspects that you touched upon are really, really important. Let's spend some time on this afternoon. Yeah. Thank you again.
Yeah.